and it was my great opportunity to get together working with Pat and his older colleague, who's now sadly died, David Smith. They're physicists by background, and they came to Keele at a time when I was sitting and working with him in something called the Centre for Science and Technology and Medicine. And that was an opportunity to meet these individuals, and we just started working together. This was something I think Pat is going to talk a bit about that. I should say Pat's a very distinguished physicist, working at, you're now Deputy Director or Director of the Czech Academy of Sciences. Yes. Right.
Thank you, Simon, not only for the introduction, but mostly for the invitation to this wonderful, I dare to say, clinical meeting. So I will just brave the serious clinical work, and I will actually show you in next 20 minutes some of the work we did with Simon Davies, which is probably so far of no clinical value whatsoever.
I disagree with that, but
I will show you that it's got a great potential. We already have, Simon's got a lot of vision, think a great deal forward. So this really should not have been called a breath ahead. It was just trying to be too clever. It should have been called miles ahead or decades ahead, because I will show that some of the results which Simon initiated 1996, almost 30 years ago, are still yet to be actually implemented into useful clinical practice. So this is our institute in Prague, physical chemistry. You see decorated with nice physical chemistry equation. I will not show any equations in my, no, sorry, I will, I have to. But I will not dwell on them. So, let me just start with some history. So, as Simon already mentioned, I had a great opportunity to do a Royal Society postdoctoral fellowship here in years 95, 96. And this was where I met Simon first. Very enthusiastic, bright-eyed young clinician, very interested in doing original research. And really, originality is what was so impressive about it. So, there was always this idea around, if we do biochemistry from blood, urine, why don't we do breath analysis for disease diagnostic and therapeutic monitoring, a term which Simon coined. And I think we have the answers now, but I will just show you the early results. So the idea is, if you can non-invasively analyze composition of breath, you can probably monitor the physiological state and do some useful analysis out of that. So, 1996, we started with a very improvised instrument, which I'm showing on the picture on the left here, which was placed in BEMP, in biomedical engineering, medical physics. And we just simply, without having a hypothesis to test, press this button here. We were just thinking, not testing a hypothesis with t-test or Markov's models. We just wanted to explore. We wanted to observe and maybe then make an inference out of the observation. So, this was the first experiment where we did not know what to expect, but Simon had, of course, a cohort of CAPD patients, also patients on hemodialysis, and we just analyzed the breath in an untargeted way, just simply to see what's in that breath. And indeed, we saw that in that breath are many, many compounds, which are highly, some of them which are highly elevated in chronic kidney disease, and which can actually decrease during hemodialysis. So, we worked maybe almost a year on this wonderful paper, Kidney International paper. I don't think I would bring it to a desert island with me because I know what's in it. I think I would not do it. If I had to choose something from Simon's work, I think I would choose something which is more clinical. But this stood the test of the time. And the observation was that in a patient with end-stage renal failure, as it was called then, ammonia was elevated 100 times above the concentration which is usual in normal population. So that was the observation, which was not really ever reported before, simply because people didn't have online techniques to analyze ammonia on breath. Simple molecule it is. GCMS, gas chromatography, mass spectrometry will not analyze ammonia. It's actually also very difficult to do biochemical analysis of ammonia in plasma. It's freezing the sample immediately on collection, etc. So this is the same data after better interpretation. This was a part of a grant proposal, and we can see many compounds: ammonia, methanol, propanol, ethanol, acetone, isoprene, phenol, and importantly amines, dimethylamine, trimethylamine, which actually are the compounds responsible for the fetor, the renal fetor. Ammonia at these levels still actually people cannot smell. And the question was, how is it possible that there is so much ammonia present in breath? Because if we do the calculation using so-called Henry's law in physical chemistry, we would have to conclude that the plasma concentrations of ammonia would be so big that it simply would be toxic to brain. So we tried to explore first by doing the experiment, actually monitoring the ammonia during hemodialysis. On the x-axis is time in minutes, something like over 3 hours of hemodialysis. And this is the logarithmic scale showing the concentration of ammonia, and it actually decreases more than 10 times during the period of hemodialysis. This is a plot showing correlation in a group of 26 CAPD patients, where the observation was that breath ammonia correlates really quite well with plasma urea, but it's not a direct measure of plasma urea. And then this is an experiment, possibly actually Simon acting as a volunteer, swilling the mouse with a solution of urea, demonstrating that ammonia actually gets elevated after the dose of urea to the mouse. I have to admit that some of the conclusions we made and we formulated in the paper were not actually quantitatively correct, but the ideas are there, 30 years ago almost. We have much more current understanding about how ammonia actually appears in breath. And basically, quickly, it's a hydrolysis of urea in saliva due to presence of enzymes, either bacterial or of other origin. And the evidence for that is that when we analyze nose exhaled ammonia, it's so much lower than mouse exhaled ammonia. And again, this was the inventiveness of David Smith, who was mentioned already, doing clever experiments, just observing what's happening. So now I just do a little bit of bibliometrics, citation analysis. This is the citation analysis only of our joint work, Spanel, Smith, and Davies. And this paper from Kidney International 1997 is now cited 312 times. But that's not impressive number as such. But what I find really impressive is that it took 20 years until people show real interest in this. So it's over 20 years, it was like 3-4 citations per year, probably most of them self-citations, one way or the other. No, seriously. But now, 2016, you see immediate growth in interest, which is really due to the development of the sensors field. People developing sensors are interested in, they call it biomarkers. Again, after education from Simon, I don't like that word too much, but measuring metabolites in breath. So there is a surge of interest in developing sensors, and I'm sure that after these sensors will be developed, then it's very likely that this will find some clinical use. Simply, these mass spectrometers, as I shown, cannot be used in clinics, even though we tried. So, keeping on the citation analysis, this is now Davies, Simon, J or not, at Keele affiliation only, ignoring the previous work. And again, you see the absolutely amazing exponential growth, like exponential with epidemics of COVID, exponential growth after year 2020, interestingly. And this is just a glitch. This is just a data analysis error because the data from year 2023 are still not fully analyzed. So all I can say, I hope, Simon, that in your emeritus role, you will continue this growth, because only now much of the work is actually really picking up. So decades ahead with much of the work. Other examples, isoprene. Observation that isoprene pre-hemodialysis, post-hemodialysis is elevated in kidney patients, and actually during dialysis it increases on average. We never could figure out why it is. Only recently last year, people in Rostock, Wolfram Maikisch and Jochen Schubert and colleagues actually understood the origin of isoprene in breast. And it's all explained here. I'm not even trying to read it, but basically isoprene is formed in muscle cells, in skeletal muscle cells. And there is genetics behind it, which explains why some people have more isoprene, some people less. This got nothing to do with like cholesterol synthesis or mental stress or anything. But still, these are solid data. This we observed, and maybe it can be reinterpreted now, something to do with muscle activity during dialysis. This was 2004, now switching into the idea of measuring total body water by deuterium dilution method. This is just a nice photograph from the laboratory, one of Simon's patients actually doing online breast analysis. So here the idea was that online is so good because you can do it immediately. In reality, it's so much more difficult than collecting samples because of the logistics, having to bring the patients to the instrument. So this was the instrument which Simon initiated the construction, so-called bedside FAMS instrument, which I think Keitan sitting somewhere there was using to a great deal. And we actually developed a method to measure total body water. Here's the simple equation, a division of volume D2O divided by a measured change in deuterium isotope ratio, which actually allows accurate calculation of total body water by isotope dilution of deuterium. This is the instrument schematics. Then we wanted to explore more. This is actually work of Keitan. Hypothesis was simple. We want to measure water overload of the lungs. It never worked, actually, because there were too many assumptions. And will I take about 5 minutes?
Just looking to see you're fine.
So this was actually, Kay put a lot of work into preparation of this experiment because this involved injection of deuterium-labeled water into internal jugular vein of hemodialysis patients. So the actual material had to be approved for this purpose, and most of heavy water is not approved for that purpose. And after doing the experiment on a group of patients, we simply calculated that the lung water would have to be something like 12 liters to explain this data. So clearly this is not the case, but we understood a lot about what's actually happening, that as the exhaled breath travels through the upper airways, it basically exchanges isotopes with water on the surface of all these mucous membranes. I was searching for pictures of Simon. For some reason, the only pictures I could find were from Cleveland 2007, which was a breast analysis summit not peritoneal dialysis meeting. And these were all the people who were actually pursuing this idea of doing breath analysis for non-invasive monitoring. I think you can see us somewhere here. And just skip this, it will be for whole lecture. Finally, I will just mention 3 compounds which actually I believe are wars for future of research in breath analysis, if anybody's interested. Pentane, which is a non-specific inflammation marker. This is a study we did on the example of inflammatory bowel disease, Crohn's and ulcerative colitis, and clearly pentane is elevated, and it can be explained by biochemistry, omega-6 fatty acids peroxidation. Another compound which I believe is useful for breath analysis is acetic acid, simply because it can be used to indirectly measure acidity of the upper airways in gastric reflux disease and in cystic fibrosis. And finally, in metabolic dysfunction associated steatotic liver disease, muscle, we believe it's worth to measure limonene and trimethylamine after giving a dose of these compounds to the patients. So the hope is that work on ammonia, which was done in 1996, will actually come to fruition in the next few years when it's combined with the development of nanosensors, whatever. And thank you for that. Oh, sorry, final word. I really want to give credit to David Smith, who passed away last year. And how to say it? He was the inspiration in this work. I was doing the technical work and all the machine building, but David was stimulating this creative work with Simon. And it's such a shame he cannot be here today, because he would thoroughly enjoy lecturing here to a group of clinicians. So, thank you.
So many thanks, Patrik. That was lovely, and you're quite right. David would love to have been here. He was a graduate from Stoke. He left school at 16. He was a graduate from Stoke, and having worked as an apprentice in the ceramic industry, when somebody noticed that he was actually very bright, he said he should go to university. So he came here to university as an undergraduate, and then actually ended up as a fellow of the Royal Society, having unpicked many aspects of ionized physics and chemistry. So he was a very interesting to talk to work with. And actually there's a direct line between the work we did on body water, measuring body water in the breath and doing that, which Richard may remember we took that portable device over to Derby, and we took it on the hemodialysis unit, and we did that here, and we measured body water in patients, and we combined it with bio-impedance measurements, which allowed us to understand longitudinally over time what happened to body composition. For the first time, actually, the first proper longitudinal study. And that led directly to the use of the bio-impedance in the BISTRO trial, which you've already heard about. So there is actually an important line of research there, which you know, I may have moved away from the breath analysis side because it was difficult.
Yes.
And I also like the way you said I was ahead of my time. I thought that was really
20 years ahead, seriously.
20 years ahead. So, any questions or comments to Pat? Yes, I think Kerry should say something. He was doing all the work in the lab at the time. My PhD student. He also.
I call myself Simon the worst PhD student. I just want to mention something that I spent a lot of time working with you three actually. That's your man probably Trinity really, David, Patrik and yourself. And I remember the time when I first started as a PhD student, and I had a lot of trouble with deuterium sourcing it, and I spent many nights sleeping with the breath instruments, far longer than I spent with my wife actually. But I just want to pay tribute to Simon, because you have the knack of just keep me going. Just kept me going, that's it. Many years actually. And even listening to study, I learned so much from you guys. So I just want to pay tribute to my mentor, only for you guys, you know him as a research collaborator, but he's my mentor, teacher, can be going for a long time actually. That's probably one of my most fulfilling scientific year of my life doing the PhD. So thank you.